last lecture was to review this funny operator, which is like the Laplacian, but on a surface. And so for the sake of students, I thought it was a good idea to do the full details of this construction by using somehow an extrinsic trick. So deciding to introduce the Laplace-Beltrami operator as the Laplace operator of the normal extension of the function. Okay, so of course, it's a matter of taste. If you like differential geometry, this approach is a little bit rough. But if you like analysis, I think it's kind of neat because you basically kill the differentiation over the surface in favor of the most traditional classical differentiation, okay? And then we discussed how to reconstruct the Laplace-Beltrami operator from the tangential gradient and the tangential divergence. So the Laplace-Beltrami operator has a nice divergent structure. And we understood that basically what goes wrong if you try to argue as in the flat Euclidean case is that your surface sigma has a mean curvature and that the mean curvature plays a role. So one of the lemmata that we used is in the last lecture was this one, that when you, so you consider the tubular neighborhood of the surface sigma, so the notation was sigma epsilon alpha, to say that you take your surface sigma and you move in the normal direction by a quantity which is epsilon times a function alpha, okay? And so when you integrate the function beta over this tubular neighborhood, in a sense, it shouldn't be too much of a surprise to discover that the integral that you get at the first order in epsilon is just epsilon times the integral over sigma of alpha times beta, or if alpha changes sign, say the positive part of alpha times beta. And I promised we were going to see a proof of that, though intuitively the reason is that you do a Fubini's theorem in a sense, right? Because beta of y at the first order is like beta of the projection. So you may think that you are moving along the surface and then transversally. So you have n-1 coordinates along the surface and then Fubini's theorem in the normal direction. So the Fubini contribution is exactly epsilon alpha, and then you integrate along the surface. Now, again, I think that if you are an expert looking at the picture, the proof is self-evident, but maybe if you are a student, it's not so clear. So I wanted to give a proof of that. Then last time there was no time to do it. But if you don't get bored, I will give the proof now. I think it's instructive for students because it's a way to learn and practice with this funny set of coordinates that was introduced, or at least widely used by Enrico Fermi, that are called Fermi coordinates, which are basically the idea is that you move along the surface and you move orthogonally to it. Okay, so how do we prove it? The first trick is that we can reduce to local coordinates. So we take a partition of unity made by some nice function phi I. So each of these phi I is smooth and between 0 and 1, and it's compactly supported within a local chart of the surface sigma, of the manifold sigma. And they have finite overlapping support, and they sum up to 1. Okay, and this is a beautiful trick because you write 1 as the sum of the phi I, So if you define beta I to be beta times phi I, instead of looking at the integral of beta, you can look at the integral of beta I, just because you write 1 as the sum of phi I. And so whatever you prove for beta I, up to a linear summation, you prove it for beta. So with this observation, I can basically prove the statement replacing beta with beta I, or if you prefer, just thinking that beta is compactly supported inside the local chart. Now, since the surface sigma is a smooth manifold, I assumed it to be C3. I mean, for this argument, you need less than that, but whatever. So locally, it's the graph of a function psi. So my notation is that I have a set big U contained in Rn-1, and locally, so locally I mean in the support of beta, or if beta I, if you prefer, in this local chart, I can think that sigma is the graph of the function psi. So at this point, I want to parameterize my tubular neighborhood with respect to the Fermi system of coordinates. That is, I take a point y in the tubular neighborhood. How can I write it? Well, I write it as a point on the surface plus t, the normal, where t is in between 0 and alpha. This is the definition of tubular neighborhood, after all. But here I'm using the fact that I know explicitly how to write the normal in the local system of coordinates. I write it in this form, given the function psi that parameterize my surface locally. Now, if I look at this expression, of course, T is just a name. So, well, the appendix of the name of the rose states stat rosa pristina nomina nuda tenemus. So I don't know whether Umberto Eco wanted to say that it's important the way we give name to things, or it's not important the way we give name to things. I'm a bit confused about literature, but for sure in mathematics it's not so important, so I can decide to call T xn. The advantage of that is that in this way I think that I have an n-dimensional object, which is y, which has a natural correspondence with another n-dimensional object, which is x prime xn, where t is just xn, okay? But it's nicer for me in my ear to think that y is a function of x and change variable as y equal to y of x, okay? So this is a nice change of variable. Actually, the first order is independent on xn, and then xn is of order epsilon because I know that t is in between 0 and epsilon alpha. So when I compute the determinant of the Jacobian transformation linking y to x, this is kind of easy because I call R to be the radical 1 plus gradient of psi square. So explicitly the derivative of y with respect to x is the identity matrix in the first n-1 blocks, and then the gradient of psi, or the gradient of psi divided by r, r-1 over r. So when I and then plus order of epsilon, okay? So when I take the determinant, the first order, I can compute it explicitly, it's exactly the radical. But the radical is also, and this is very nice, because this radical is also locally the surface element. So if I think as a change of variable, so the volume element dy, this is a Lebesgue volume element. The Lebesgue volume element dy is just the Jacobian determinant times dx, but the Jacobian determinant produces naturally the surface element given by the radical. So I can consider the first part here as a surface element, and then I have plus order of epsilon, fine. So the reason for which I like this change of variable is that, if I'm able to, okay, I'm able to change page. I like it because I can look at the object I have to compute, that is the integral of the beta I over the tubular neighborhood. As I was saying, I can project y on the surface, and I lose something that is going to be infinitesimal in epsilon. Then I do my change of variable. So I think that y is actually y of x. So for the change of variable I had in the previous page, I write this as the surface element multiplied by the xn. Now I integrate over xn and I get exactly epsilon alpha. And then I have the smaller reminders like little o of epsilon. Okay, so this is just, if you like, the formalization of the proof by picture in a sense, but I think it's a nice exercise to familiarize with the Fermi coordinates. So this somehow completes the part of the first lecture that was remained unfinished due to the fact that I'm too slow and I want to do too many things. But then with this lemma in hand, so I like a lot this lemma because it allows me to get rid of surface integration as much as possible, right? Again, it's a matter of taste. If you are very good in geometry, of course you like surface integration, but to me surface integration is like swimming in the ocean, that you have big waves and you unexpectedly float around, you don't know where you are going. While, for instance, if I feel more confident with Lebesgue integration because there I have a thick neighborhood and I can use divergence theorem as a strong weapon as much as I want. So the idea was basically to prove a bunch of theorems that were related to surface integration, somehow avoiding differential geometry, but just relying on real analysis. Because instead of integrating on the surface, which is like swimming in the ocean, we thicken a bit the surface into a tubular neighborhood. We used our real analysis there. We were free to change coordinates there, to use the divergence theorem to integrate by parts and get a bunch of useful identities. So the first identity that we proved was this tangential divergence theorem, which is like, if you like, an integration by parts, because you place the tangential divergence from the vector field phi to the scalar function, to the vector field f to the scalar function phi. So you get up to a minus sign, you get a tangential gradient. So this part, the last part, f dot, the tangential gradient with the minus sign, is the one you would expect because it's the analog of the integration by parts in the Euclidean setting. Since for me here sigma has no boundary, but there is an additional term which I would say it's not so easy, at least for me, to see if I don't look at things carefully, which involves the mean curvature H. And so this additional term for us was found using the divergence theorem in the classical sense, and of course being a little bit careful with the normal. But basically, you see the main ingredients of the proof were the previous result on the thickening of the surface into a tubular neighborhood and the standard divergence theorem. Okay. Once we have the surface integration by parts, the tangential divergence theorem, then we are in a good shape. We get for free a number of cool identities such as the Minkowski integral formula. which is just a particular case, if you like, of the tangential divergence theorem, we were able to prove that the Laplace-Beltrami operator is self-adjoint, which again is a particular case of the tangential divergence theorem. And then we investigated a bit more on the mean curvature. So we found an explicit formula for the mean curvature with respect to the graphical structure of the surface. From this, we deduced the useful corollary that is somehow a maximum principle for the mean curvature, or a monotonicity of the mean curvature with respect to set inclusion. If one set is included into the other, then the mean curvature of the set inside is bigger than the mean curvature of the set outside. Of course, this is kind of evident in dimension 2. Then in higher dimension, you may argue taking sections to compute the mean curvature, like an average of the sections, or you can use the explicit formula that we discussed before. As an obvious but useful corollary of the monotonicity of the mean curvature, we obtained that if you have a bounded set, there exists always a point which has a strictly positive mean curvature. And you just, to prove this, you just touch your set with a ball from outside. And you use the comparison principle given by the previously mentioned monotonicity. Okay, then we finished our analysis of the Laplace-Beltrami operator. Well, there was also another remark later on, I think, that we will review. So I wanted to put a warning, because at least for me, the Laplace-Beltrami operator is very dangerous because it's hard to see it sometimes. And it's easy, for me at least, to make a silly confusion between the Laplace-Beltrami operator and the tangential Laplacian. Okay, the tangential Laplacian would be just taking two derivatives in the tangential direction. So you take the full Laplacian, if you like, and you remove two derivatives in the normal direction. Whatever is left is two derivatives in a basis of the tangent plane. And you may think erroneously that after all, this Laplace-Beltrami operator is just the tangential Laplacian. But this is a mistake, because in this, one loses exactly the term coming from the mean curvature. So there is an additional term that is the mean curvature times the normal derivative of u. Okay, and the proof of this was straightforward, but more than the proof, I think it is inspiring to look at what happens in a concrete case, for instance, in a two-dimensional case in which you just have a sphere, and you see easily from the computation we discussed last time, why the tangential Laplacian, that in this case is just the tangential second derivative, for instance, in the vertical direction at this point P, is different from the Laplace-Beltrami operator of the circle, which would be just the Laplacian of the projection of the extended function. Okay, so you can relate the tangential divergence and the Laplace-Beltrami operator to objects of Riemannian geometry, and we commented on that, saying that it's actually useful to look at this coordinate expression because it tells us that for simplicity I took the manifold to be smooth, but once you write coordinates, you realize that it's enough to suppose that the manifold is C2. Okay, but if you want to work extrinsically, it's better to have one derivative more, because in this way the normal is C2 and the projection is C2 and so on. Okay, so as a byproduct of the previous formula, of this formula here, of the relation between the Laplace-Beltrami and the tangential Laplacian, we get the classical formula of the Laplacian in spherical coordinates. So let me stress that this term here, h times the normal derivative, is essential. You don't have to miss it, because it's the one that in the Laplacian in the spherical coordinates is producing the term related to the first derivative. Okay, so usually many courses you prove this formula just for rotational invariant functions. But we proved it more generally if U is not necessarily rotational invariant. And I think we finished this discussion on the Laplace-Beltrami operator by writing the Laplacian along level sets. So we discovered that the Laplacian on a level set is just the second derivative on the external direction, on the external normal direction, but plus the mean curvature of the set times the normal derivative of U. And this is a formula that is kind of important, that it's used very frequently when you have to analyze the behavior of a function with respect to its level sets. Now I'll show you, of course, there is a mini course in this B1 minus school given by Julie Clutterbuck from Monash University, and she will give a much more intense and advanced and interesting course about understanding the level sets of the solutions of elliptic and parabolic equations. So her course is really devoted to this topic, so it's much more interesting and much more advanced. But I think that this formula here is maybe the first ingredient towards the understanding of this beautiful and very rich and very difficult topic. Okay, with all this material in hand, we were able to prove the sub-bubble theorem. So if you have a smooth and bounded domain in Rn, whose boundary has constant mean curvature, then this is a necessarily a ball. So the proof we gave was based on a bunch of integral identities that were deduced basically from our analysis on the Laplace-Beltrami operator. That is why I wanted not to skip the details of the Laplace-Beltrami operator, because it's something that sooner or later one has to see it. So I think that for a student, sooner or later means the sooner the better. There is no way to escape from making our hands dirty with the computations related to the Laplace-Beltrami operator one way or the other. So it's better to see it once and for all. And okay, so we use this previous knowledge of geometric identities, but also we used a beautiful trick based on the introduction, well, of course, of a deficit. The deficit that was somehow the difference between the square norm of the Hessian and the square of the Laplacian. This was a positive quantity, and when this quantity is zero, then the Hessian is going to be proportional to the identity. So this is a remarkable fact. And the second remarkable fact is that we were able to reduce the study of the geometric problem given by the sub-bubble theorem to an analytical problem given by the properties of the solution of a nice elliptic partial differential equation. So this is, I think, so from my personal point of view, it's a beautiful thing, right? Because for many of us, dealing with geometric objects is extremely difficult. So if you think about in the sub-bubble theorem, you have a set. So what is a set? So for me, it's a pain to think about a set, the mean curvature of a set. You need to have a very strong geometric intuition. The fact that you can reduce the problem to the solution of an equation may make our life easier. So I think that it is a great conceptual progress whenever we can change a geometric problem into an analytic one. Well, of course, it's also progress when you can change an analytic problem into a geometric one, provided that you develop an intuition, a geometric intuition on the problem, okay? But for instance, in this case, it was so convenient to reduce the problem to the function big U, because on big U, we had for free several integral identities that were just coming from the previous work and a few integration by parts that basically led us to three useful inequalities. And the reason for which they are useful is that you always try to make one of these inequality to be an equality. So an inequality that becomes an equality. So this, my English is not perfect, so but I think you understand what I mean, right? You don't want an inequality, you want an equality, okay? And the reason for which you want equality is that equality holds if and only if the domain is a ball. Okay, so you have reduced your geometric problem on omega on a bunch of inequalities that if one of them happens to be an identity, then you are done. Okay, so for the particular case of the sub-bubble theorem, there was this idea which I think dates back at least to Antonio Ross to exploit the so-called Heinze-Harker inequality. Well, the Heinze-Harker inequality is just Cauchy-Schwarz, if you like. But once you have Heinze-Harker inequality and you use the previous results, in a couple of lines, you can prove the sub-bubble theorem. And this is basically what we did in the last, in the first lecture. And we are now ready to reuse this material for the rest of the course. So in principle, I was ambitious and I said, okay, let's do the Laplace-Beltrami operator in full detail, from which we deduce the sub-bubble theorem. And then we discuss the isoperimetric problem, and then the Serrin's problem, and then the Saint-Venant's problem. Okay, let's see if we can really complete the project. So for the isoperimetric problem, let me say this. So in the isoperimetric problem, I think I will overdo. So there are easier ways to discuss the isoperimetric problem, but I would like to introduce the machinery that is needed if I want to treat at the same time also Serrin's problem and Saint-Venant's problem. So let's discuss what I will do and why this is even too much for the isoperimetric problem itself. So the isoperimetric problem is to find, to classify the sets which have a prescribed volume and the smallest possible surface area, okay? So for this, I introduce a bunch of technology. So first of all, I compute the first variation of the area function. So somehow, if I have to discuss what the smallest possible surface area means, well, I will have to consider a set, to consider competitors for this set, and somehow I have to consider a smooth family of competitors, so a family depending on a parameter, and then I want to take derivative with respect to this parameter described in this family. So for this, I have to put my hands into the differentiation of the area of a surface, okay? So the lemma is the following. So you have a diffeomorphism, a local diffeomorphism that is the identity for short times, then the first order, I call it theta, and then higher order in t. And I call omega t to be the map at time t of my initial set omega. And everything is very smooth, so in principle, I think that I can consider the surface measure of my set omega t, and I can take derivatives in t. And the t equal to 0 first derivative, it's written here, it's just the integral over the boundary of omega of the mean curvature of omega times theta, which is the velocity field of the vector field, scalar the nu. So if you like, it's the external flux of H times the derivative of the diffeomorphism family. Okay, let's briefly look at the proof. Of course, the experts know it, but I think that not all the students do. Again, you can reduce to local coordinates, and so you parameterize your the boundary of omega by some function f that maps Rn-1 into Rn. And so you know that the metric is given by the scalar product between the ith and jth derivative of f. And so I also call f tilde to be the composition between the diffeomorphism at time t and the map f. So f tilde is the parametrization of the local parametrization of my surface element at time t, obtained just by composition in the obvious way. So corresponding to this f tilde, I have a new metric that is g tilde ij, which is again the ith derivative of f tilde, scalar product, the jth derivative of f tilde. Okay, so please stop me if there is anything unclear, or if I'm saying something silly or whatever. So the objective for me now will be to use this new metric to compute the surface area of the evolving set, and I will develop this new surface element in T to compute the first order. Okay, so as simple as this, or as technical as this, because of course when you have to compute first orders, well, it's what it is, right? So the G tilde J is known because the F tilde J is just the composition. So if I have to take derivative of F tilde, well, I just use the chain rule. So when I use the chain rule, I get the G tilde ij is the original Gij plus some Tmij, and the Mij is what you get by the chain rule. So when you do the chain rule, you have to take into account derivatives of the composition, but remember that if you differentiate in X the diffeomorphism, at the zeroth order you have the identity. So at the first order you have to match the identity with the velocity, well, with I and J respectively, and then you will have higher order terms. So the first line is just the chain rule, and of course I separate the order 0 from the order 1 and from the higher orders. Okay, now when I take the derivative of G tilde, then it's just so whether the determinant of the matrix G tilde, this is just the determinant of G at the order 0, plus the matrix that I obtained from the first order. So for instance, at least I would do the computation like this. I would take the matrix G as a common factor, so that the determinant of G tilde would be the determinant of G times the determinant of the identity plus T, the matrix that is given by the inverse of G times the matrix M. And then I take that determinant to be 1 plus the trace, and this is exactly what I wrote here. Okay, so this is just linear algebra of the determinant of a perturbation. You can do it in several ways. I said how would I do it, but of course there are other ways to compute determinants. You may prefer to do it other way. Okay, so very good, because I know that the area element locally is the square root of the determinant of the matrix. So if I do the square root of this object, I get the square root of the determinant of G. Then when I develop the square root of 1 plus x is 1 plus x over 2 at the first order. That's why I have these 2 here. Okay. And then I write explicitly who Mij is. Well, now the 2 simplifies, because Mij has 2 pieces, but since they are contracted against Gij, which is symmetric, the 2 pieces give the same contribution, so the factor 2 cancels. And okay, and here you just realize that DIF, DJF is precisely Gij, and so here you get exactly the tangential divergence of theta. So if you remember last lecture, there was a slide in which I said, well, if you want to put coordinates, the tangential divergence is exactly this object here. Okay. Well, so you're pretty much done, because the area of the perturbed set is just at the first order the area of the original set, which is what we expect. Then we have a first order, which is given by the tangential divergence. But now you use the tangential divergence theorem and you reduce it exactly to h times the velocity in the normal direction. So the external flux of h times the velocity. And so this proves this little lemma. Okay. So the reason for which I needed this lemma is that since I want to look at the isoperimetric problem, I want to take a set and I want to move it by vector fields, by some diffeomorphism generated by vector fields, which have zero flux along the original set. So this is a little bit tricky, of course, because I'm somehow prescribing these vector fields only along the boundary of omega, but then I want to move the full set omega, not only the boundary. So I need a way to create a diffeomorphism, a nice diffeomorphism using only the vector fields at the boundary. So this will be somehow the first technical ingredient I have to handle. And the second technical ingredient is that I have to understand functions which have zero average with respect to these zero flux vector fields. So one is to get a zero flux vector field and milk out a family of diffeomorphisms. And the second thing is to understand what it means to be orthogonal to the zero flux vector fields. Okay, so the first of these two problems is solved by this lemma. Okay, this lemma is just implicit function theorem. Again, I will do this. I will state the lemma and I will discuss it with you. Then, if time allows, I will give the proof later. Okay, because it's a bit technical, but it's just implicit function theorem after all. So let's see the statement and let's convince ourselves that it's more or less obvious. Let's also convince ourselves that it's not as obvious as it seems. Okay, so the thing I'm looking at are vector fields that have zero flux on the boundary of omega. This is the condition that will be on my side for probably the rest of these lectures. So theta is just defined, you see from the picture, on the boundary of omega. So it's not necessarily a tangent vector field, so this happens to be tangent, but for instance, this is not tangent. I wanted to draw something that may look like zero flux, because these ones are getting slightly out, this is tangent, this is getting a lot in, this is getting a lot out. So all in all, this in my picture wanted to be more or less zero flux, okay? So the idea is that you can construct a family of local diffeomorphisms in a neighborhood of omega that are, well, of course, at time t equal to 0, nothing happens, and then you move with velocity t, and then higher order, and then phi preserves the Lebesgue measure. I mean, intuitively, it's clear that you expect something like this, because if theta is zero flux, that was I was saying, points here are pushed a bit outside. This point is pushed outside, but this point is pushed a lot inside. So after all, from this picture, you see that whatever you lose because you go outside, you gain because you go inside, and vice versa. This is what you expect by a zero flux vector field. Now, strictly speaking, it's not so obvious though, because you have an object, the vector field, that is defined only on the boundary, while you would like to have a diffeomorphism that is defined on omega. Because think about, if you want to deal, for instance, with the isoperimetric problem, you want to take your full set omega and to move it around, preserving its volume. So you would like to use the vector field defined only on the boundary of omega to produce something that looks like a continuous deformation, not only of the boundary, but of the full set, and possibly in a neighborhood of the full set, okay? So we will postpone the proof of this lemma. Of course, if this looks obvious to you, okay, you don't need to go into the details of the proof, but let me say that, for instance, to me, it sounds plausible, but not completely trivial, okay? But it's true, I mean, we will prove it together, but at the first glance, it's something that maybe some of the students could have some reservation to buy a statement like that. And we will go through the proof later on, but the proof is implicit function theorem. The second statement that I would like to give, this is much simpler, is the following. So suppose that you have a function, for instance, a continuous function, such that whenever tested against the normal component of a zero flux vector field is equal to 0. Well, then if this is so, then f is necessarily constant on the full boundary of omega. Okay. The proof of this is simple. Well, it's basically functional analysis, right? What is orthogonal to the flux of the zero flux vector fields? Well, only the constants. Okay, but let's do the proof, because again, it's a bit tricky if you have never seen this argument before. So one way to prove it is that I choose, well, there are probably many ways to prove it. Okay, so I will give a constructive proof whenever possible. I like, rather than appealing to abstract functional analysis, I like to hammer down the proof with an explicit construction. So in this case, let me do an explicit construction. So I choose the vector field theta obtained in this way. I take f minus its average in the exterior normal direction. Okay, this is a vector field. Okay, and interestingly, its average is 0. So its flux is 0, because whenever I average against the normal, well, the multiplication with the normal is going to give me 1, and then when I average, I get the average of f minus the average of f times 1, which cancels. So theta by construction is 0 flux. Okay, then I can use my hypothesis. So I know that the average, the integral, or the average, when I put this dash here, it means the average. But of course, if the integral is 0, so the average is 0. But I like to compute with the average because it's nicer and simpler. Okay, so when I take this average by assumption, this average is 0. But I know that theta is just this expression here. So I multiply f by f, I get f squared. Then I have f times the average of f. And then by the linearity of the integrals, I have that this is the average of f squared minus the average of f squared, because I average and I get this there. Okay, then of course, I try to complete the square by adding and subtracting, and I see that this expression is actually the average of a square given by f minus its average. Now, the fact that this quantity is 0 and this integrand here is actually non-negative means that f has to be equal to its average, and so in particular, f is constant. Okay, so this proves this little lemma, the one that I call lemma 2. Okay, with this, we are able to prove the isoperimetric problem. So the isoperimetric problem is that the set that is minimizing the surface area among all, say, connected nice domains of class C2, you can relax the regularity assumptions, but I'm treating here the easiest case just to be able to develop some confidence with the computation. So I don't want to go into the more abstract geometric measure theory under the isoperimetric problem. I'm doing the classical and easy case, and I'm somehow assuming that the minimizer exists. So you come to me and you say, oh, I have a minimizer. What can you say about it? Well, I can say that the mean curvature is necessarily constant. And the proof is simple because you take a zero vector field along the boundary of omega, and you use the first lemma to construct a family of measure-preserving diffeomorphism. Okay, so from lemma 1, you know that such a family exists, and then you use the fact that the derivative of the evolution of the surface measure is equal to the normal flux of the mean curvature times the velocity of the diffeomorphism, which was theta by construction. Okay, so I'm using here the lemma 1, which is this one, to say here that I have from a given vector field theta on the boundary of omega, I have a family of diffeomorphisms that move not only the boundary but the full set, preserving the measure. Then in this way I have a competitor. So if omega is minimal, or even if it's a stationary point for the surface area with respect to sets with the same volume, then the first derivative is going to be 0. So here I'm using minimality, or if you like, a criticality of the minimizer. Here I'm using the lemma, yes, right? I'm using here the fact that I know how to compute derivatives at the first order of the evolution of the surface measure. Okay. Okay, but then I have that the integral, okay, I have repeated twice equal to 0 just because I wanted to stress that this quantity is equal to 0, and it's equal to 0 for every zero flux vector field. So I can use the last lemma, this lemma 2, to say that H is necessarily constant. Okay, so this proves the corollary. Well, to be honest, as I was saying, I was too verbose. There are quicker ways to prove this that I left as an exercise, give simpler proof that do not rely on the construction of suitable vector fields. And the reason is that the isoperimetric problem has such a nice scaling property, because the volume scales like a power to the n, and the surface scales like to a power to the n minus 1. So just using scaling, you can find competitors which would lead you to the same conclusion as the corollary. You don't really need the construction of the vector fields, but I will need it later on anyway. And the construction of this vector field is an important ingredient whenever you do analysis, because you like to construct vector fields and you want to do it once in your life and then forget about and use it whenever needed. Okay, and whenever needed means in the next lecture for sure, for instance. Okay, with this we are done, because we can use the subbubble problem, the subbubble theorem, and complete the proof of the isoperimetric problem. So the isoperimetric problem tells me that if I have a minimizer among all nice connected bounded sets that have prescribed volume, yes, here I forgot, I said everything, but not that prescription, that are connected bounded of class C2 and with a given volume, of course, then the set omega is a ball. Okay, And the proof is just use the previous result that tells me that this set omega has constant mean curvature, and then use the subbubble theorem that we proved in the first lecture to say that if it has constant mean curvature, that it is necessarily a ball. Okay, this completes the isoperimetric problem, unless we want to prove this this vector field property. Okay, so again, it's a dirty job, but someone has to do it. Let's do it. So the idea is to use implicit function theorem. So first of all, you know, I like extrinsic things, so I don't like to work with vector fields defined just on the boundary of omega. The boundary of omega is too small for me. I define the normal extension of the vector field just by projection. Okay, so up to considering the normal extension, I will identify theta with the vector field that is not defined just on the boundary of omega, but it's defined on a tubular neighborhood of the boundary of omega. And also I can multiply by a cutoff function, so I can also think that theta is 0 outside the small neighborhood of the boundary of omega. And same for the normal. So also the normal for me is a vector field that is defined up to extension outside the boundary of omega as well. And I put the normal equal to 0 after a bit of a tubular neighborhood. And why I want to do this? Well, because I want to look at an ODE problem. So basically, I take the solution of an ODE with the velocity theta starting at a point x. Okay, so I use t as the time for this ODE problem. And then I use another parameter s that is in this way. So I take a function that depends on the point x, t and s. I take the first component, which is the flow generated by theta, and then I take a second component, which is the normal direction weighted by the parameter s. Okay, the reason for which I want to do that is because maybe it's true that theta was 0 flux, but it's not so obvious, and maybe not even true, that the flow generated by theta is going to be volume preserving as it is. I may want to change it a bit in the normal direction to make it a bit outside or inside, outer or inner, to compensate some loss or gain of volume. Okay, so maybe this for the way I defined the ODE, I made my set fatten a bit, then I have to put it on diet and shrink it a bit using this additional direction. Okay, so it's a dirty trick, but it's something that we cannot really avoid, because since the vector field was defined only around the boundary of omega, I don't think there is any way to avoid a trick like that, because it's somehow arbitrary the way we extended the set theta outside omega. Okay, so this is a tricky thing if you come from dynamical system, because you think, oh, of course, if I have a volume preserving flow, this flow is going to have 0 flux on the boundary of omega. This is fine, but remember that here we are doing the converse. We are starting with the vector field, which is defined only on the boundary of omega. So the way we decide to extend it outside and to produce a flow by an ODE says very little on the measure preserving properties of this flow. of course, a posteriori you think, well, but when t is small, this thing must be more or less measure preserving. Well, more or less, but I don't want it more or less, I want it exactly. So that is the reason for which I want to correct this construction in the normal direction. Okay, so how do I correct it? Of course, I define big F of t and s to be the Lebesgue measure of the image of omega under the function that depends on t and s. And I use the implicit function theorem, okay? So I'm able to go down with the page. So first of all, I compute f at time 0. Well, f at time 0 is the measure of little f at time 0. And of course, I change variables, so I call y to be f of x at time 0 s. But at time 0, this is just x plus s nu. So if I take the determinant of this, the determinant of this will be 1 plus s, the divergence of nu. If you remember, nu is also a vector field which is extended everywhere. Well, it will be 0 outside a tubular neighborhood of the boundary of omega, but in principle it's defined everywhere. Okay, so the reason for which I like this expression is that now I'm free to use the divergence theorem again. So I have the boundary of omega plus s nu times nu, which is 1. Okay, I think that someone is making fun of me because I use the divergence theorem even to prepare tea in the morning. Yeah, so I use the divergence theorem again and again. Okay, so of course, nu times nu is 1. And so here I have the measure of the surface of omega. And then I have computed f at time 0. So the Lebesgue measure of the evolution with respect to s, s is my correction, at time 0. Okay, this means that I can take derivatives in s at s equal to 0. So if you see the first order, so basically you have a constant, which is the volume of omega, and then the first order in s is just the area of the boundary of omega, which is a number, it's not 0. Okay, so the derivative with respect to s is just a number which is not 0. So I use my, my implicit function theorem to say that given small t, I can find a function, say gamma of t, with gamma of 0 equal to 0, such that f of t, gamma of t, is equal to f of 0, 0. Okay? Okay, so now I define phi of xt to be my little f at time t with this additional parameter s equal to the gamma of t. Then by construction, you see that f preserves the Lebesgue measure because the Lebesgue measure of f of xt gamma of t is by construction this big F. And this big F is equal to f of 0, 0, which is exactly the Lebesgue measure of the set omega. So by construction now, this f preserves the Lebesgue measure. Okay? And also the first order was unchanged. So our physical intuition coming from dynamical systems was not bad after all. We were saying, oh, for the dynamical system is obvious. Well, it's obvious at the first order. The first order was good enough to preserve the Lebesgue measure, in the sense that if you take now the right diffeomorphism that preserves the Lebesgue measure, you take the velocity of this, well, you do your change rule, so you differentiate in t, and then you differentiate in s, but you put also the derivative of gamma in t. Well, when you take derivatives in t, you look at the definition of f, right? The definition of f, when you put s equal to 0, you take the derivatives in t, you get exactly theta. That is the friend that you want. Yes, you get theta, that is the friend that you want. Then you have your derivatives in s at time 0. So the derivative in s will be precisely nu, because at time 0, this is x. If you take the derivative in s, you will get nu. Okay? And so here you have gamma dot of 0. So my handwriting in the slides is very bad. There is a dot here, but it's almost invisible. So this is gamma dot of 0. There is a dot. It's not your screen that is dirty. There is a dot, but it's very, very tiny. So it's almost invisible. Okay. Okay, so let's get rid of this additional term. So in principle, we would like the velocity at 0 to be only theta, not nu gamma of 0. So we better get rid gamma dot 0. We better get rid of gamma dot 0, but this we can do it again because we look at f of t0. This is the converse computation that the one we did here. So here we did f of 0s. Now I want to do f of t0. Okay, but the proof is the same. So I change variable. I remember that when s is equal to 0, my function f is just the ODE flow. So when I do the Jacobian, I will have here the divergence of the velocity of the ODE, which is precisely theta. Now, guess what? I integrate by parts. The fact that I get here theta dot nu, but if you notice, up to now, I didn't really use that theta was 0 flux. So if I want to prove that the measure preserving diffeomorphism that I constructed as theta as first order, and I want to use my intuition of dynamical system properties, well, now it's time to use that theta is 0 flux. So this contribution here at the first order actually vanishes. So this is important because it tells me that the time derivative at 0 is equal to 0. So it's true that I'm doing the same proof as before, right? It seems that I'm repeating this argument, but I'm not really repeating this argument because this was for S and the new one is for T. And there is a huge difference because when I differentiate in S, I get something that is not 0. But when I differentiate in T, due to the 0 flux condition, I get something that is 0. Okay, this is good in the sense that I can write f of 0, 0, which of course does not depend on t. So when I take derivatives, I get 0. I use the volume preserving property. So the volume of t gamma t is constant. This is the volume preserving property that I found. Then I use again the chain rule. So I differentiate with t, then I differentiate with s, and I get the gamma dot. Again, there is a dot here that is almost invisible, but it's there. So the partial derivative in t is 0 because of this computation. The partial derivative in s is the one that I computed here. So it's just the surface volume. And sorry, here for silly reason, I wrote the surface of B1, but should be the surface of omega. So this is just a typo. Well, a posteriori, I wanted to I wanted omega to be the ball, but here I did it too quickly. This is just a typo. This is the boundary of omega. But nevertheless, this is an object which is not zero. That's the only thing I'm using here. So gamma dot is zero. But this means that I can go back to this computation and get rid of the last term here of gamma dot of zero and obtain that the velocity of my diffeomorphism is actually equal to theta. Okay. So very good. So this now completes. This now really completes the isoperimetric problem. Well, as I said before, if you are smart and you use the scale invariance of the problem, you don't need this sophisticated construction of vector fields, but you will need it for other things. So I decided to put it here because it was a nice test to upskill our knowledge of flows and vector fields and diffeomorphisms and vector fields. Okay, so I'm not sure I will be able to complete the discussion about Serrin's overdetermined problem. Also, in Brazil, you have a number of super experts of this problem, so I'm not saying probably much new, but okay, so let's start this this discussion on Serrin's overdetermined problem. So I think that Serrin's problem is beautiful for several reasons. One of the reasons for which I think it's an incredible theorem, it's because it's a theorem from real life. So there was this professor in engineering, which is Roger Fosdick at the University of Minnesota, who was a colleague in the same university, though I think a different department, of Jim Serrin. And well, I never met Fosdick, but I think he was an extremely smart person. And even if he was not a pure mathematician, as some people would say, he knew mathematics in a very, very deep way. Actually, today I bumped into a paper by Fosdick about Almanzi's formula on higher order Laplacians. And again, so the person was really interested in a bunch of mathematical questions and differential equations, and he was able not only to prove theorems, beautiful theorems on that, but also, and I would say more importantly, to settle the right questions. So my modest opinion is that good mathematics is not the mathematics that closes a subject, it's the mathematics that opens a subject. So this guy Fosdick posed to Serrin the right question that opened a whole subject. So, of course, Serrin had all the merit to solve the question and to invent the beautiful method that was used millions of times after him. And he had the merit somehow to provoke also the proof by Weinberger of at least a particular case of this result. But I want to really spend a few minutes to remember this pioneering view by Fosdick, who was able somehow with this scientific curiosity to open these beautiful fields of research. So posing two beautiful questions to Serrin. Well, there are two questions if you think about physics or engineering, but they are just one question if you think about mathematics. This is a great advantage of mathematics, which is unifying. So you have different questions, but once you have the right mathematical formulation, you end up with a solution that comprises and encompasses them all. So the two questions were, one, motivated by engineering. So you have a straight bar subject to torsion, and you know that the traction along the surface is independent of the position. And the question is, can you determine the shape of the bar? The second question was motivated by fluid dynamics. So you have a straight pipe in which you have a viscous, incompressible, and irrotational fluid flowing. And you know that the flow of this fluid produces a constant tangential stress along the pipe. Can you determine the shape of this pipe? The beauty of mathematics is that once you settle the problem into a mathematical framework, you just have to look at an equation. The equation somehow is the same torsion type equation that we used in the first lecture for the soap bubbles problem, right? In the first lecture, we introduced the function that we called big U. In that case, that was the solution of Laplace of U equal to 1 in omega, U equal to 0 on the boundary, okay? So these first two lines would reduce to the function big U that we used in the proof of the soap bubble theorem. Okay, but the problem of Fosdick is somehow more rigid than that, because it says that not only you have an equation in omega and the Dirichlet boundary condition on the boundary, but you also have an additional condition. The additional condition comes from the traction being independent of position, or if you think about fluid dynamics, comes from the fact that the tangential stress on the pipe is constant. Okay, so you have an additional condition that is of Neumann type along the boundary of omega. So of course, not many domains omega admit a solution of this type. So the theorem of Serre is actually more general. This is somehow a particular case, say due to Weinberger, if you like, and I will basically present a variation of the proof of Weinberger using the material that I introduced so far. So the theorem by Serre is that if omega admits a solution of this equation, then omega is necessarily a bond. Okay? So I think, I think that it's better again for me to stop here in case people have questions. So the goal of the lecture tomorrow would be to give the proof of this statement, to give one proof. There are millions of proofs of these statements, and they are all beautiful. The good thing of Serrin's problem is that, again, beautiful problems are the ones that not only do not close a subject, but they open a subject, but they allow reinterpretation of the same theorems that reveal newer and newer insights. So I think this is the typical example of one of these problems. I will present one proof, but there are many, and they are all deep and beautiful, and each of them reveals a new aspect of the problem. So I probably stop here, and tomorrow we prove Serrin's problem, and we discuss a problem of engineering and elasticity that is related to Serrin's problem, that is called the Saint-Venance problem. And